To understand the antidysrhythmic medications better, the best course of action is to expand our understanding of the cardiac conduction system slightly, but this will actually make it easier to understand. So to start, I'm going to go into slow channels and fast channels. Slow channels are the SA and the AV node. They are called slow channels because depolarization is dependent upon calcium, which enters cells a lot slower than sodium does. In fact, you can see it on the phase 0 here, which is the depolarization phase, which isn't a straight line up, but a curve. Like the action potential you are used to, it also relies on a slow leak of sodium into the cells to reach the threshold to depolarize, and also like the action potential you are used to, it is reliant upon calcium leaving the cells to repolarize. So in short, what you need to remember about the slow channels is that they are the SA and the AV node, and that they are dependent upon calcium to depolarize. The fast channels are everything else within the cardiac conduction system, such as the bundle of His, the bundle branches, the Purkinje fibers, the pathways from the SA to the AV node, and the branches going into the left atrium. To review them, here we have the slow leak of sodium into the cells until they reach the threshold, which then causes a rapid depolarization of sodium rapidly entering the cell, a small calcium kick, and then calcium continuing to enter the cell while potassium leaves the cell to maintain the plateau, and finally calcium leaving the cell to repolarize. So for fast channels, what you need to remember is that they are sodium-dependent depolarization, and they are every part of the cardiac conduction system except for the SA node and the AV node. So let's look at EKG a bit more detailed in terms of what's going on within the heart. Here we have the SA node firing off, the atrium contracting, the AV node building a charge, firing off that charge, and then that charge going through the ventricles until the ventricles repolarize. But we can make it a little more simple. Here we have the fast channel, we have the slow channel of the SA node firing off, the fast channel of the atrium, the slow channel of the AV node, and the fast channels through the ventricles. Again, remember that slow channels are calcium-dependent depolarization, and fast channels are sodium-dependent depolarization. And as you can see here, the PR interval is mainly slow channel dependent, and the QT interval is mainly fast channel dependent. Here we can overlay the different action potentials over the EKG and see how they work. Here is the action potential for the SA node, the action potential for the atrium, the action potential for the AV node, and the action potential through the ventricles. Now let's get into the meds. Class 1s are sodium channel blockers, which is a term for them I'm not very fond of, because type A and type B aren't pure sodium channel blockers. Type A does block sodium channels, but it also blocks potassium channels. Type B only blocks sodium channels once the membrane is positively charged. Type C is our true sodium channel blocker. Class 2 are the beta blockers, Class 3 are the potassium channel blockers, and Class 4 are the calcium channel blockers. If you're looking at previous slide and at what is slow and fast channels, you can see that the Class 1s and the Class 3s go together rather well, as do the class 2s and the class 4s. An easy way to remember this is evens with evens and odds with odds. So here we have the class 1 type A antidysrhythmics. The easy way to remember this is class 1 type and potassium. So for this, the sodium channels are blocked, which lengthens the rapid depolarization, and potassium channels are also blocked, which lengthens repolarization. So where does this have an impact? Well, a lengthened depolarization of sodium channels will widen the QRS complex because it takes more time for it to depolarize. And a lengthened repolarization will mainly impact the QT interval because, again, it takes longer for repolarization to happen. And through these, we have a slower heart rate through both. The class 1 type B's, easiest way to remember it, is class 1 type but only positively charged. I'm going to spend the most amount of time with this medication because it's a little hard to explain, and when you look at the action potential, it actually seems like it would make the heart rate faster, but it doesn't. So essentially this medication has two actions. First, it prematurely knocks down the action potential from a positive charge. So here we have the normal action potential, and here we have the positive charge getting knocked down faster, which pushes it into the repolarization phase quicker, which actually shortens the action potential, but it doesn't do so by much. In fact, if you're looking at an EKG, you probably won't see any real difference in the QRS complex. But what it does do is it increases the absolute refractory period. And if you remember what that is, it's the period of time in which a cell cannot depolarize again. So how does this work? Well, the class B meds only bind to sodium channels when the membrane is positively charged, which is anything above this line. When you first introduce the med, anything below here, it's not going to bind to sodium channels. But the medication does take some time to unbind from sodium channels. It actually does so relatively quickly. In fact, it does so fast that if you have a normal heart rate, then none of the sodium channels will be bound by the time that action potential is ready to kick off again. However, it doesn't do so fast that if you have a tachy rate, that it will be completely unbound by then. So essentially, if you have a tachy heart rate, it'll bind here, stay bound, it'll start to unbind here, but it won't be completely unbound by this point, which is where the normal absolute refractory period ends. Some of it will still be bound. It will still impair the sodium channels, which essentially pushes the absolute refractory period to the right over to here, which then a longer absolute refractory period means that there's a prolonged time before another action potential can prematurely kick off. This is how it slows heart rate. Type C's are our complete sodium selective blockers. I like to think of them as the only true sodium channel blocker because they go after all sodium channels. And they do so regardless of the membrane charge. So not only do they inhibit sodium channels during the rapid depolarization phase, they also inhibit them during phase 4, where there is a slow leak of sodium across the membrane, which you can see here, and see here for the fast channels, and you can also see here for the slow channels. So how does this work? Well, on the EKG, again, a slower rapid sodium exchange will prolong the QRS complex because it takes more time to accomplish. And further, because there is a longer phase 4, it prolongs the time before the slow channels, which aren't dependent upon sodium for depolarization, but are dependent upon it to reach their threshold, can fire off again. And next we have the class 2s, which are the beta blockers. Beta blockers reduce sympathetic stimulation of the heart cells. The two parts of the cardiac conduction system that are the most receptive to sympathetic stimulation are the SA and the AV node, which means it will mainly impact the slow channels, which, if you remember, are the ones or that make up the majority of the PR interval. So less SA node and AV node excitability means there's less channel opens and there's a slower depolarization, at least in relation to a tachy heart rate. And again, slower depolarization means a slower heart rate. Next, we have the class 3s, which are the potassium channel blockers. Both fast and slow channels transfer out potassium to repolarize. Slowing repolarization will therefore shift the repolarization line of the active potential to the right, which makes it take more time to reach the absolute refractory period cutoff. This has the majority impact on fast channels because in most cases slow channels repolarize a lot faster than they are ready to kick off again. However, the exception to this would be something like AFib, where they are depolarizing so fast that extending the refractory period would actually have an impact. Finally, we have class 4s, which are the calcium channel blockers. They work in kind of the same way as beta blockers. The difference is that beta blockers reduce excitability to prevent more channels from opening, whereas calcium channel blockers actively close channels. But in terms of the EKG, they'll have